Welcome everyone to the Steve and Sylvia Burges Endowed Lecture in Civil and Environmental Engineering. My name is Bart Nijssen, I'm the department chair. Steve and Sylvia's involvement with our department goes back more than 50 years, when Steve became an assistant professor in 1970. That was followed by a long and productive career in teaching, research, and mentoring of junior colleagues. As I was preparing these introductory notes, I looked up Steve in our purple book with the departmental history. Many of you don't know that this exists, and it also stops in 1999, but I have a whole document over the first century of civil engineering. Okay, as I was looking in that book, I couldn't help but smile when I read the following anecdote. It's really short, it's a one-liner. In 1993, Steve gave a keynote address to an international conference in Canada, where he challenged the conference participants with characteristic wit to write fewer and better papers and to read more. For those of you who know him, that should not come as a surprise. To this day, I receive periodic emails from Steve with recommended papers, still exhorting us to read more. As chair, I directly see the tremendous support that Steve and Sylvia provide to the department, and I'm deeply grateful for that support. Which brings me to today's lecture. It's actually the second Burges Lecture in one calendar year, right? Because the last one was actually in February by Dawn Lehman. But we kind of moved it around a little bit, and it just worked a little bit better in the fall, so we have two in this calendar year. We also have a number of previous Burges lecturers in the audience today. Dennis Lettenmeyer in the back was the first Burges lecturer, and Mark Benjamin is sitting here as well, so welcome. Today's lecturer is Julian Marshall. Professor Marshall received his BSc degree in chemical engineering from Princeton University and graduate degrees in energy and resources from UC Berkeley. Julian did a postdoc at UBC up in Vancouver, after which he became faculty in civil, environmental, and geoengineering at the University of Minnesota. In 2016, he joined us here at the UW as professor.
Do you want to work on developing solutions that can make a difference, using the real world as a classroom?
During his time at the UW, Julian has developed the Grand Challenges Impact Lab, or GCIL, which is a quarter-long program in Bangalore, India, that offers an active hands-on learning laboratory for students from the University of Washington. He has authored more than 170 papers in peer-reviewed journals, and his work is widely cited. For example, last year he had 3,000 citations alone. Professor Marshall's research is an exposure assessment, understanding how much pollution people breathe and how to reduce those exposures. In recent years, Julian and his team have published a number of high-profile publications in leading journals that have documented the differential exposure to air pollutants for communities in the US. This work, the systemic disparities that it reveals and how to address them, form the topic of today's lecture. Please hold your questions till the end. After the lectures, we'll have a brief Q&A, and after that we'll have a reception in the Walker Ames room, which is on the second floor on the west side. And with that, please join me in welcoming Professor Marshall.
So thank you all for being here. I'm going to open with two quotes. The first quote is, "Not everything that is faced can be changed, but nothing can be changed until it is faced." That's from James Baldwin. And the second quote is, "There are no new ideas. There are only old forgotten ones, new combinations, extrapolations, and recognitions from within ourselves, along with renewed courage to try them out." That's from Audre Lorde. So there are no new ideas. There are no new ideas in my talk here today. All the things that I will say have already been said by Audre Lorde and others. I'm just extrapolating those ideas into the area that I work on, which is air quality engineering. I'm still learning, so if you see opportunities where I can do better, if you see mistakes, please let me know. I look forward to hearing from you in the Q&A after. So I'm going to talk about air quality modeling, and there's a question mark in my title, and that's because I'm still working to understand what does that mean. I'm going to start with a land acknowledgement that we are on the land of the Coast Salish people, and as well with a slavery acknowledgement that the racial oppression is a part of our history. The exploitation, mistreatment, genocide, white supremacy, all those things that underlie these two statements form the context for and underlie the air pollution disparities that I'm going to talk about today. So in air quality engineering, probably the main reason why we care about air pollution is because of the health effects, which are quite large. I study this topic, and every day I'm constantly surprised by how large are the health effects from air pollution. So here are some estimates from the global burden of disease for the United States. These are the most recent estimates that they have on their website. And you can see, okay, we have tobacco, high blood pressure, and so on down this list. Welcome to junior high health class. If you scroll down this list, air pollution is on this list. It's not number 1 on the list, but it's on a top 15. And the numbers here by these estimates are several tens of thousands of deaths per year. What I want to argue today is that in addition to this being a main reason why we care about air pollution, there's also the equity aspects, the distributional aspects of who is more exposed and who's less exposed, and that forms its own separate reason, its own ethical reason for caring about air pollution, and perhaps even a different set of ways of thinking about addressing air pollution, data and models that would be needed to focus on not just the averages or the totals, but also what are the disparities and how do we address those disparities. Now, I had this word anti-racist in my title, and this may be a term that you're familiar with or not, but here's a quote from a well-known book by Ibram X. Kendi, and I'll just read this quote out. A racist policy is any measure that produces or sustains racial inequity between racial groups. Whereas in contrast, an anti-racist policy is the reverse, any measure that produces or sustains racial equity between racial groups. Okay, and then here's the core point. There is no such thing as a non-racist or race-neutral policy. If we are observing inequities that we see and we let them exist without examining them, without trying to address them, that is, by this framing, by the framing I'll use today, not okay. We need to focus on them and see what we can do to address them, and not really let them be part of the system unexamined. And then the last part of the quote: being an anti-racist requires persistent self-awareness, constant self-criticism, and regular self-examination. And again, if you see opportunities where I could do what I'm doing better, suggestions for improvement, I welcome them. I'm going to lead with my conclusions. There are 3 core conclusions to my talk today. And the first is, we don't all breathe the same air. As Bob Bullard has said, America is segregated and so is pollution. The segregation reflects our history, reflects laws and planning, violence and threats of violence, which have led to the segregation we see, not only of people, but of where the pollution is. So I'll talk about that. That's the first bit. We don't all breathe the same air. The second conclusion is that the past is present. The disparities that we see today, some of them are caused, yes, by decisions that happened recently. However, many of them are a reflection of decisions that happened a long time ago, decades ago. And those decisions lead forward into the system that we have today, the exposure we have today. And then the third conclusion is the inequities will not eliminate themselves. If we are unhappy with the disparities that we see and we want to address them, the current tools and approaches that we have are unlikely to address them directly. We may need a separate set of models and data and ways of thinking about air pollution which specifically focus on those disparities. Okay. So here's a couple maps of Seattle. You may be familiar with this. On the left, we have redlining, a term that's familiar probably to most people. This was an action of the federal government to back home mortgages, and one of its main impacts was to reinforce existing racial segregation. So this is a top-down example of systemic racism. On the right side, you have racial covenants. This is basically when you bought a house, in the language that what you're agreeing to is you would not sell your house to someone else of a certain racial group. And here we have a map of Seattle. In both cases, you can go and read the language behind the redlining and behind the racial covenants. Here's at the bottom here is one example from a neighborhood, a house near me. The language in there is explicitly racist. It will make anybody in this room's blood boil. It is unbelievable and offensive and quite recent. So let's talk about the time frame. The start times for these two processes, the sort of top down and the bottom up, are not in my lifetime. These are not in my parents' lifetime either. My parents were born in the late 30s, early 40s. So this is like my grandparents' generation that was around when these systems were enacted. That's the origin of them. Now the end of them, it's kind of hard to draw a clean line in the sand, but for Seattle, I've done the best I can with when these policies ended. There were different Supreme Court rulings and whatnot, but for Seattle, there was a state bill, it's very short, you can go online and read it, forbids lending standards with no economic basis. Kind of amazing that we needed the legislature to tell banks that they were supposed to only care about economics. That's the bill, that's 1977. And then forbidding kind of racial covenants, here we are in marvelous, wonderful, liberal Seattle. Well, there was a public vote to end this practice, to outlaw this practice, which failed widely by 2-1. That was in the mid-60s. It wasn't until a few years later, after Martin Luther King was assassinated, that the town council said, nope, we're not putting this for a vote, we're just making the rule, and we're forbidding this. You can't do this anymore. So the end of these rules, at least by law, is now in my lifetime, in the lifetime of many people in this room. Now, of course, when these rules were passed to outlaw this, that the racism that underlied these rules didn't instantly go away. So here's an example of an ad in the Seattle newspaper at the time, advertising basically it was a restricted neighborhood. There were racial covenants in this neighborhood, and that's why you should come and buy this home at a time when this should have been illegal. I want to make two other points about this. One is this map of redlining, air pollution is correlated with redlining. So we've done a study looking nationally at air pollution levels, and with Professor Shepard, who's here in the audience, we've looked at concentrations here in Seattle. We see the same result, that there are disparities in contemporary air pollution reflecting red line codes, which are decisions that happened many decades ago. So we didn't ask for this. These are sort of parts of our cities that were handed down from decisions that are realistically generations ago. And the last point I want to make about redlining, people talk a lot about redlining. This is not just about redlining. There's sort of a lamppost problem, right? The lamppost problem is like you go and study what's under the lamppost because there's light there. And there's not light a block later where there's no lamppost. Well, the same thing for redlining. These are maps that have survived to today. They've been digitized, we can study them, and that's why there's a lot of research on the redlining maps. But there are lots of other maps. There are lots of other systems in place before, during, and after redlining. So banks had maps, other parts of the federal government had different maps. We have looked a little bit at some of the other examples of infrastructure that came along before or after redlining, and you see disparities today as well from those other bits of infrastructure. So redlining is just sort of the main one that people point to, even though it's just one example. Okay, so with that as background, there's this term environmental justice. So what does that term mean? Well, it means various things, many different things in different contexts to different groups. You can think about urban or rural, remote locations, indigenous communities, nuclear energy, both the fuel and the spent fuel. You can think about climate change, global environmental justice, right? There's many different contexts of what this term means. In an air pollution sense, when I go to the literature about what does this term mean, I kind of divide it, the definitions and the investigations on this 2x2 axis. Local, systemic, and then outcome versus process. So when you look to the definitions, if you have definitions that are down here in process, right, process is about how are decisions made, who makes decisions, who has access to decision makers. And in those contexts, you'll see terms like fair treatment and meaningful involvement. And in terms of outcomes, which are things like concentrations and risks, then you'll see terms like undue burden or disproportionate impacts. So for today, and in my research, I'm up here, and today's talk will focus on this upper right quadrant. Outcomes, so I'll be talking about air pollution concentrations and risks. And then looking systemically. Okay, now one reason why I look systemically is is this. There's this expression, all politics is local. And in environmental justice contexts, a lot of the focus is on what happens locally in this one specific situation, what's happening there, the history in that specific location. And the details of what happens in that one location obviously can be very, very important for understanding that one local context. However, it's also the case that often what happens in one location is not unique. It reflects patterns that happen over and over and over and over again in our society. And so in the research I'm looking at, I'm trying to look systemically at, if you step back from any one specific example, what are the broad patterns you see across our society? It's funny, when I look at this, the history of environmental justice can be, they can have a long history, or it can be quite recent. It kind of depends on who you are and where you sit. But a lot of this is in the lifetime of many people in this room. So, in the late 60s, there were several civil rights laws that were passed. And about a decade later were the first examples of applying the civil rights laws and the community organizing approaches, applying those things to environmental problems. And so you see in the late 70s and early 80s, protests around hazardous waste facilities in North Carolina. You see activism in Chicago. There's a lawsuit. Bob Bullard was involved in kind of the first lawsuit. At the time, his then wife was suing around trash dumps in Houston, all being located in the smaller number of minority communities. So he was studying this in Houston on sort of the lawsuit side in the late 70s, published on this in the early 80s, and then spent much of the 80s showing how this pattern was repeated across much of southeastern part of the US. He then published his book, Dumping in Dixie, in 1990. So that's kind of the early bits of environmental justice in the 80s and 90s. There were kind of more convening and conversations about this. Maybe some of you remember Bill Clinton passing this executive order and the optimism that came around this executive order in 1994. At that point in time, there was still not a lot of research on this topic. So you can see there's a couple lit reviews. In the early 90s, just a handful of studies. By the mid 90s, maybe a few more. Not a lot. And there's various reasons for that, which we can talk about. Why is this a topic that was not highly studied at that time, and who cared about this topic, and whatnot. But one of the reasons that underlies this is that the mapping software to do the kinds of analyses you would want to do were not widely available then. When Bullard talks about the work that he was doing, he said, it was like using like a chisel and stone to write with. It was just really quite manual and not facilitated by the kinds of analyses that would be routine today. So, ArcGIS, this all kind of changed right around 2000. So ArcGIS had just come out then. QGIS came out a couple years later. Shapefiles were sort of invented. Google Maps came out a few years after that. Like a lot of things changed right around 2000 and in the few years after that, 2000, 2005. And so for me, in the arc of my career, I was also part of that. I entered grad school in 2000. And here's some work that I was able to do. Maybe it would have been a lot harder if I'd entered grad school at a different time or a little bit earlier. I was looking at exposure assessment, exposure to air pollution in Southern California for a group of about 10,000 individuals based on a survey that had been done there. And there were 4 racial ethnic groups in the survey that I was studying: white, Hispanic, African American, and Asian Pacific Islander. And these are the pollutants that I was looking at: ozone, diesel particles, and benzene. And so what I'm showing here is the median inhalation intake of that pollutant for each of these 4 subpopulations relative to the overall population median. So 0 would be you're kind of at the average, cleaner or dirtier. And what we see is for these 2 pollutants, for diesel particles and benzene, white people have lower exposures than average, and the 3 non-white groups that I'm looking at have higher exposures. And then for ozone, the reverse pattern holds. Now, if this were an air pollution class, I would ask you why do we see this? And the answer is this follows directly from the chemistry and physics of where air pollution comes from and how it's transported in space. So these two species are what we would call primary pollutants, meaning that they are emitted directly, and the high concentrations are near source. In this case, this would be near downtown Los Angeles and along freeways. And those are locations that, on average, have fewer white people and more non-white people. Whereas in contrast, ozone is not emitted directly. It forms in the atmosphere from chemical reactions of precursor emissions. And those reactions take a little while to happen. As well, when you're right near the source, there's additional chemistry that actually titrates the ozone away, reduces ozone concentrations. So for both reasons, the concentrations of ozone are not high near the source. It's actually a little bit downwind. In the Southern California case, that would be kind of eastern suburbs. And so just based on the chemistry and physics of where the pollution comes from, you get these reverse spatial patterns. And what you see up here is kind of what you would expect based on the chemistry and physics. So when I finished this study, I was in grad school from 2000 until 2005. The study came out soon after my PhD. Southern California is an interesting case study. There's a lot of data there. It's an important case study. It also may be a unique case study. And I was curious, I'm interested in the systemic aspects. Is this repeated elsewhere? So to answer that question, we did two things. The first is we did another literature review. So now this has been a few years later. There was kind of this explosion in environmental justice research in the early 2000s. So we then found hundreds of articles, not just dozens, but hundreds of articles that were out there. And the vast majority of them, not 100%, I mean, I'm showing here you've got 3 pollutants and 1 pollutant goes the opposite way, but the vast majority reported higher impacts to racial minorities and to low SES, socioeconomic status, individuals or populations. So this is one way to look systemically, is to look at repeated studies done with probably different methods and different data sets in many, many locations. And I was also interested, what if you use the same methods? What would you see then? Now, at the time, it was not really possible to do that kind of analysis nationally for the following reason. If you go based on models, in general, the models at this time were quite spatially coarse. And the measurement data from EPA was also spatially coarse. Even today, if you go to the EPA website and you look for a map of what's the air pollution near me, you will typically see this sort of multi-state region. So that's too coarse to pick up this sort of near highway, not near highway effect. In fact, even EPA monitoring stations today, if you look at, it depends on the year, it depends on the pollutant, but a typical median number of monitors per urban area in the US is 0. That's the median number of monitors in an urban area. Then if you have so many areas are not monitored, some areas are monitored, you get 1 or 2 1 or 2 stations. Sure, you'll get places like Los Angeles where you have many stations, but most places don't have enough stations to really pick up the spatial variability. So the first thing we had to work on was developing an approach to looking at air pollution nationally that gave better spatial precision. And we turned to an approach which is called land use regression, which is quite common today. At the time, it was relatively new and had only been applied at urban areas. And we developed the first national land use regression model, which gives you spatial coverage, complete coverage, and also with great spatial precision. Basically, you take the EPA measurements, and this is a method, you could think of it as machine learning. We use machine learning, we also use other techniques, but it allows you to make predictions at all the locations where EPA does not make measurements. So this is what we see when we do this. Here I'm looking at a pollutant NO2, and for 2 census years, the year 2000 and 2010, this is a conventional engineering box plot, so it shows the percentiles that are the 10th, 25th, 50th, 75th, and 90th percentiles, and then the mean. You can see over time, the air got cleaner by roughly a factor of a third or so, factor of 2, something like that, about a third cleaner from the year 2000 to 2010. Thank you, EPA. Thank you, Clean Air Act, for this improvement in air pollution. And then these predictions were at the census block level. That's the smallest spatial unit that the census offers. So we can start to divide things up amongst different subpopulations. So here we have 4 main demographic attributes: race, ethnicity, household income, education level, and age for the same years, 2000 and then 2010. So to point out a few things, one is when you look at differences amongst subpopulations, that's mainly happening in this box. When you look over to the other boxes, there's not a lot of differences amongst the subpopulations. There's some interaction here between race and income, and I'll get to that in a minute, but in general, this is where you see the largest disparities. And we looked at other demographic attributes as well. You kind of see the same story, that it's mostly about race ethnicity. And the second part I want to point out is just how things changed over time. So across each of these boxes, between the earlier year and the later year, everybody's air got cleaner. Even where there are disparities here, everybody's air got cleaner throughout all the distribution, throughout all the subpopulations. So that's the good news. Again, thank you, EPA. We should celebrate that victory. That's important to note where there are successes. However, the disparities remain over here compared to the earlier year. In fact, the absolute difference between the most and least exposed population has come down. The air got cleaner, but the relative differences are nearly unchanged. So you can imagine, just like as a thought experiment, if you could just wave a magic wand and take all the air pollution outside and reduce it by a factor of 2. All the concentrations get cut in half. Okay, everybody would benefit from that change, and yet it would leave completely unchanged who is more exposed and who is less exposed. The absolute difference between the most and least exposed groups would come down, and the relative difference in this sort of magic wand sense would be unchanged. And what we see happening is not so dissimilar from that, where over time everybody's air is getting cleaner, the absolute disparities come down, but the relative disparities don't. Now this is one way of looking at the data. This is by subpopulation, so my unit of analysis here is a subpopulation. Another way to look at this is in space, where my unit of analysis is neighborhood, or in this case it's a census block group. So here we have the same 2 census years plus 1 year earlier. We have the percent non-white in the community there, in the neighborhood. In each of these lines, the dot is the median, the thicker line is the interquartile range, the 25th to 75th percentile, and then the 10th to 90th percentile. So if we just follow the dot for a moment, the dot over time is coming down and to the right, reflecting that the air is getting cleaner and our society is becoming more diverse. The slope of this line, or the difference between the left and the right, represents the inequalities that we see. So over time, this line is coming down. It's getting flatter, and yet the disparities remain. In the final year, there's still kind of roughly a factor of 2 difference between the left side and the right side. So the same story here. Things are cleaning up. Everybody is benefiting. That's the good news. And yet, the disparities remain. There's more work to be done. Now, when I present this kind of information and the information in the previous slide, the first question I often get is, well, what about income? Are you sure this is really differences by race? Because in our society, race and income are correlated. And so is this not just differences by income that are masquerading as differences by race? And the short answer is no, not really. That's not what's happening. So here's a look at this. I've divided now the same NO2 data for 1 year. I took people who live in urban areas and divided them into large, medium, and small urban areas. This is just based on thirds. So 1/3 of the urban population is here, 1/3, 1/3, and then rural areas. And we do this is kind of important because the income distribution and the pollution levels differ between large and small cities. So in each of these 4 plots, the x-axis is income level, the y-axis is the same pollutant, NO2 air pollution, and then I've subdivided it into the 4 largest racial ethnic groups that are in the census, white, black, Hispanic, and Asian. So essentially the slope of this line represents the differences by income, and the gap between the lines represents the differences amongst racial ethnic groups. And when you compare amongst these, you have disparities in both fronts, right? Higher income leads to cleaner air, and race also, there's differences by race in air pollution with white people having the cleanest air, at least here in the large urban area, one that I'm pointing out. The differences by race ethnicity are larger than and statistically distinct from the differences by income. So it's not just that the differences by race are merely differences by income. If you compare at low income or at middle income or at upper income, you see differences by race ethnicity, and they're nearly unchanged across the different income levels. In addition, you can see you have cleaner air for low income white individuals than you would, for example, for upper income Hispanic individuals. So, and if you kind of go through all these numbers, we've stared at these numbers a lot, the differences by race ethnicity are larger than and statistically different from the differences by income. The differences by race ethnicity are larger. Okay, so here's one pollutant, NO2. This is a criteria pollutant. There's a lot of research on this. It's not the only pollutant we care about. So we've looked at various pollutants. Here's some maps for 3 different pollutants, NO2, which is what we've been looking at so far, ozone, and then particulate matter smaller than 2.5 microns in diameter. In these plots, so here's the difference between the average exposure for white versus non-white people in each state relative to the overall national average. You can see there's differences amongst states, there's differences amongst pollutants. Actually, the differences amongst pollutants is exactly what you expect from the chemistry and physics, similar to the earlier slide. Ozone is secondary, concentrations are more spread out in space. NO2 is primary, or it's nearly primary, so you get the most spatial variability. You have the most opportunity for disparities to arise because there are larger spatial gradients. And PM2.5 is kind of in the middle. It has a primary and a secondary component. The levels of spatial heterogeneity are kind of intermediate, and the disparities that we see are intermediate between NO2 and ozone. In this map, the gray is sort of nearly zero difference. Then you have more purple means higher exposures for non-white people, and then this yellow color would be higher exposures for white people. So we've made lots of maps and looked at different pollutants. Here's the different criteria pollutants. Here's different racial ethnic groups. The main thing I'll point out, there's 2 things. Of course, there's differences by racial ethnic group. There's differences by pollutant. In general, if you look to the column for non-Hispanic white people, you see that things are either about equal. The white color means plus or minus 5%, so nearly equal, or cleaner air. Whereas if you look for where do people have dirtier air, it's over on this part of the curve. So it's generally non-white individuals who are breathing dirtier air if there is a gap. And the other thing I'll point out is this is an issue for all of the states. There are no states that are not colored in somewhere in all these maps. So just a couple summaries here, some takeaway points. In most states, 73% of states, exposures are kind of greater than 0. I use greater than 5%, higher than average for black people. For Hispanic people, the number is 57%. For Asian people, it's about 1/3. And for white people, it's none. There are no states in which the most exposed group is white people. The most exposed group is always a racial ethnic minority group. So this is the systemic part. These are the patterns that are repeated over and over again across the US. The maps down here are all kind of one pollutant at a time. You can also start to look at multi-pollutant approaches to these same data. So here's one example. The proportion of the US population that is living in a very polluted location, above the 90th percentile, for 4 or more criteria pollutants. These are really polluted locations. Some people might label these the sacrifice zones. So what are the demographics in those locations? That population, that's about 5% of the Hispanic population, about 2% for the Asian and black population, and under 0.5% for the white population. Okay, and I'm going to show you one result which is not for the US. I'm going to step outside the US context. I had a graduate student who was from China, was interested in the same questions, but for China. So we went through the same process, developed a national land use regression for China, then started looking at disparities by demographic attributes. Now, of course, what are the demographic attributes that you look at are quite different. The meaning of race is quite different in China. There's different aspects that make up socioeconomic status. And what we found, we looked at this in various ways. What we found over and over again was the opposite as what you see in the US. So here we have different measures of socioeconomic status, and there's different ways of doing this. We once we found one result, we kind of wanted to look at it again and again and again to make sure it wasn't anomalous, and we kind of see the same pattern. We looked at different pollutants, NO2 and PM2.5. We looked at urban areas and rural areas and migrant populations, and we see the same thing over and over again. These lines all slope up, meaning higher SES means higher pollution levels. All right, now why is that? Well, this is really a study of what, not of why. But we can try to shed a little bit of light on the why aspect just by seeing what's happening. I mean, the most obvious answer is that China is at a different place in its development process. And in China, economic development brings industry, which brings pollution and also brings income. And so there are spatial correlations. The areas that have more industry are higher SES, and are more polluted. And this is a national look. We also subdivide this by each individual state, by urban areas, and so on. We see that this pattern repeated over and over again. So, everything is different in China. The economics, history, demographics, culture, planning, etc. I put this up here as a reminder that the patterns that we see in the US are not necessarily the way it has to be. It doesn't have to be this way necessarily. It's just the way it is, the way it happens to be. And that reflects culture and history and all these other things. And I hope that means we might be able to change it. Maybe, that's the hope. Okay, I'm going to shift gears a bit in terms of research questions and methods. So the methods I've been talking about so far use these empirical models or land use regression models, which make predictions about concentrations and how they vary in space and time. And if we want to talk about solutions, if the disparities are something we don't want to see, we want to address the disparities, change the disparities, then we need to start looking at how would we change concentrations. In air quality engineering, there's really only one way to do that, which is to reduce the emissions. That's the one tool we have. There's not really direct remediation of air pollution, you just reduce the emissions. So air quality engineering is like a prioritization exercise of which sources to reduce and by how much. And so I'm going to shift methods to mechanistic models that are based on chemistry and physics that give us attribution. That is, we can attribute the concentrations back to sources because we're modeling cars and trucks and power plants separately. And it can also let us ask what-if questions. What if we were to reduce the emissions from this source or that source? How would that change the concentrations, and how would that change disparities? So to address the disparities, it's going to take a lot of different ways of thinking about the problem. Right? It's going to take lawyers and economists and urban planners and many other groups, and also an understanding, I believe, from the science and engineering standpoint, the air quality models, to understand which sources to target and by how much. So when we do that, when we use these kind of mechanistic models, there are different sectors of the economy. So here we have kind of all the emissions. The models that we're using, since there are some modelers here in the audience, these are Eulerian grid models. What that means is your reference frame is fixed and the pollution blows through. We have emissions in each time step and we have chemical reactions, and we can make predictions about concentrations and tag it back to sources. So here are the different sectors of the economy, road dust and light duty vehicles and so on. The model that we're using has relatively good spatial precision and is relatively computationally light, which allows it to run the model many times. And you can see that each of these different sectors of the economy would have different spatial footprints as to where the pollution is from those sources. In the first study, when we were working on this, we have different sectors of the economy. We started working with economists to look at this question up here. Who causes versus benefits from these activities? And the economists that we work with used a survey, which we then adopted, which looks at the end use and the end consumer of these goods and services. And the survey that's used here, there are 3 different racial ethnic groups that are in the survey, Black people, Hispanic people, and then everybody else. So that's what we have here, and then we separate out consumption by government and then exports to other countries. So just to kind of give a framing here, in a typical framing, if you have a plant that's making something, I don't know, pens, then you would attribute the pollution from that factory, you would attribute that pollution to the factory that makes the pens. And that's kind of what's in the databases that we use, the conventional air quality engineering databases, the National Emissions Inventory, which comes from EPA. And by making these connections, we're looking at who consumes the goods and services that lead to pollution. So if someone purchases a pen, then we're tying the pollution from the pen manufacturing plant, in this case, to the person who consumed that goods or service. And so sort of asking, what if that person were quote unquote responsible? Or if we were referencing the pollution to that person. Okay, so here's the inputs to this analysis. The outputs come in 2 different parts. This is the first part, so the exposed part. We have here the same 3 racial ethnic groups that were in the survey, Black, Hispanic, and then white/other. Here's our concentrations, lower for white people, higher for Black and Hispanic people. Here's the overall population average. If you've been paying attention so far, this does not surprise you at all. The difference is, because we're using a mechanistic model, we now have attribution. So we have these different colors, we can say which sectors of the economy led to these exposures. This is the first half of the coin. The other half of the coin is this, what I'll call, it's caused. Who consumed the goods and services that led to that pollution? And here we see essentially the reverse pattern on the right as we saw on the left. More consumption of goods and services by white/other than by Black and Hispanic people. This is per capita. This is already accounting for differences in population size. Now, I argued already that this side of the result is not an economic story. These disparities, yes, economics matter, but largely these disparities are race, ethnicity. Whereas in contrast, this side of the plot very much is an economic story. The reason for these differences are different levels of consumption. If you look at the details, there's a slightly different basket of goods consumed by the different groups, but really the main driver is just levels of consumption, which leads to more goods and services and more pollution. Okay, so when we finished this paper, we said, all right, well, we have attribution. We know the sectors of the economy. And so what we really should do is figure out which sectors of the economy are leading to these disparities. Because if we do that, then the policy implications are pretty clear. If you want to address the disparities, then target those, one or two or three sectors of the economy that are really like driving the disparities. Okay, that was kind of our research question for the next step. Now, it turns out that framing was really naive. It's not like that. It's not like there's just one or two or three sectors of the economy that lead to the disparities. It's like they all do. So here's some results. Here we have the same 14 sectors of the economy. We have here non-Hispanic white people, then everybody else, which we label people of color, and then the three largest group that make up this everybody else category, Black, Hispanic, and Asian. On the x-axis is the percent exposure disparity and the percent of the total exposure. So if you kind of multiply these two things together, you get the area, which is what your eye sees here and notices which are larger. And so these are kind of ranked from highest to lowest in terms of the area would be, to what extent does that sector of the economy contribute to your unequal exposures on average for these subpopulations? In blue means lower than average, and in red means greater than average exposures. And the point of this slide is, on this side over here, there's an awful lot of red. In fact, for this column here, for Black Americans, it's not just most of them, it's all sectors of the economy lead to higher than average exposures. Another way to say this is systemic racism is systemic. When all the tens of thousands of sources that are out there located wherever they did, there was millions of reasons why they chose to locate wherever they wish to locate, but there's this forcing function. On average, they're more likely to locate in an upwind of Black and brown communities. This partially reflects political power, right? Sources are more likely to locate in communities that have less political power to fight against those sources locating there. Okay, so what we see here is actually most emitter categories yield unequal exposures. It's not just one or two or three of them. The figure that's shown here is the overall national average. We really tried to divide this up in different ways and see if there was just one aspect that was really driving these results. One set of US states or urban conditions, or just we divide this in various ways, and we see the same pattern over and over and over again. It's like it was planned this way. So these results hold across many dimensions, by US state, by urban area, by rural area. Same thing, you've seen this before, that the disparities in rural areas are just not as large. We still see them there, but concentrations are cleaner, and so the overall disparities are just not as great by different income levels and by different exposure level. So when we saw this result, then we said, oh, if we target different sectors of the economy, that's not gonna work. We're gonna get what we saw already, which is we're going to leave the disparities in place and we'll clean up everybody's air. That's the good news, but we won't address the disparities because by targeting sectors of the economy, all of them lead to unequal exposures. So we finished this project and we thought, oh, what we really need is location-based, not source-based emission reductions. The source-based emission reductions, like the sectors of the economy, if you're familiar with the Clean Air Act, that would be like the MACT and BACT type standards. Those standards go after different sectors of the economy. So we thought, okay, how can we do this in a location-based approach? And can a location-based approach address the disparities that we see? Okay, so for the next project, that's what we did. We looked at three different ways of thinking about this. The first line up here is using an ambient concentration standard. In the Clean Air Act, these are the National Ambient Air Quality Standards, the NAQS. And so these yellow lines represent enforcing a NAQS. The blue line is going by sector of the economy, and the green line is going by location. And then what's plotted here on the y-axis on this left figure is the concentration disparity. It's the concentration difference between the most exposed racial ethnic group and the overall population average. And what's on the x-axis is the cumulative emission reduction. This is for pollutants that lead to PM 2.5. So you start off on the left at 0. This is sort of like the start of your simulation, present conditions, no emission reductions have happened. And then over here, your emissions have been reduced to 0. In fact, we start up here, this is like current conditions, no emission reductions and disparities of what they are today. And if we were to just reduce all of the emissions proportionately, 1%, then 2%, then 3%, on down to 100% reduction, then we just march down this dotted line. And the disparities would just march down to 0. You would not get to 0 disparity until you got to 0 emissions, and then everyone would be breathing clean air. So what we see is the National Ambient Air Quality Standards type approach. Your goal is to reduce this y-axis value to 0. And your goal is to do that as quickly as possible. Can we eliminate the disparities? So this yellow line doesn't get us there. We do not eliminate the disparities with this NAAQS type approach. And one of the reasons is that the NAAQS are generally enforced over a pretty large geographic area. And so you kind of are more likely to get this same thing you've seen before, which is the concentration has come down for everybody. The blue and green lines are optimizations. What we said is, what if you use this approach, but implement it in the most effective way you can, so that every action you take is designed to reduce this y-axis value, these disparities, as quickly as possible. So here we choose the pollutant and the sector of the economy which leads to the most rapid reductions in this y-axis value and the disparities. And what you see is you can eliminate disparities, but you have to get to basically 0 emissions before you do it. So this blue line can do it, but it's not very rapid. It's not super effective. Whereas in contrast, this green line, going by location, optimizing by location, gets us there very quickly, almost overnight. This is like less than 1 year's worth of emission reductions, if placed in the optimal locations, would eliminate the disparities. So these two lines, these are optimals. Of course, any real policy would not follow the sort of modeled optimal policy. But we use this to say, these are the two lines that represent what's in the Clean Air Act, and they will not get us there, we don't think. Whereas this green line, which is not really an approach that's in the Clean Air Act, is what would be needed to address the disparities in this kind of theoretical model. The other plot over here is the population average. So this is the disparity, that's sort of like equity versus efficiency, whereas here's the average. And what you can see is the story is not so dissimilar over here. The green line is at the blue line or is better than the blue line. So that tells me that by picking the green line, by going for locations, it's not like there's some trade-off between these two. We can do well for equity, and we also can do well to improve everybody's air pollution at the same time. Now, in some ways, this conclusion is not new, right? This is the same thing that overburdened communities have been saying for years, or decades, or generations, which is, please clean up the air pollution in my community. And here we have some modeling results that say the same thing. That's the approach that we need to take if we wish to address disparities. Whereas if we keep doing what we've been doing, these main two tools in the Clean Air Act, we're likely to continue to get what we've been getting, which is improvements in everybody's air pollution, but without really eliminating the disparities. So the last thing I want to talk about is some kind of current events in the air quality and environmental justice sense, which is the Biden administration's Justice 40 approach. So under this approach, the idea is that 40% of the benefits from investments in addressing climate change would fall to overburdened communities. And that's the goal. And then there's this tool, which is a CGIS tool. It's a mapping tool that sets up where those investments will be located. And of course, we're already spending lots of money. Tens of billions of dollars are flowing through this initiative to the communities that are identified in the CGIS tool. And at first, when we entered this analysis, we thought, oh great, this is the location-specific policy that we want to see. Let's see what this is going to look like. Okay, so I have two plots on this. Going forward, so we have first a business as usual before this Justice 40 analysis has been implemented. So here we just looked at historic changes in emissions over time, and we forecast them 20 years into the future. So here's our start year, year 0 out to year 20. We have in each of these lines here, so you have by disadvantaged communities or DACs, that's what is established by this tool under Justice 40, the CGS tool. So these are census tracts. Right now it's binary. You either are or are not a DAC, a disadvantaged community, by the rules of this tool. The dotted line is what's happening to the overall average. Then you have DACs and non-DACs over time. Then here's by different racial ethnic group. Again, the population average and our 4 racial ethnic groups, and then by income, low income versus not low income. So what you see over time in our predictions is kind of what you've heard has happened historically. Everybody's air is getting cleaner. These lines are approximately parallel. We're not really getting much reduction in the inequalities, and the disparities are largest by race ethnicity and kind of smaller by these other two. Okay, then we said what happens if, because of these investments, emissions are reduced more rapidly in DACs, in disadvantaged communities. Okay, so it's a busy fair. We'll step through this. Here's what we see. This is looking, the orange line is current, and then you have our predictions in 20 years under the business as usual. So these two are what you saw on the last slide. And then we have with the policy in place with DACs. And what we said is what happens if in DACs, the medium blue is in those communities, emission reductions are double the prior rate or quadruple the prior rate. Double is sort of like the 90th percentile of the distribution if you look across space, and quadruple is like the 99th percentile. So this is sort of aggressive and very aggressive emission reductions in DACs. In the upper row here, you have the absolute disparity in PM 2.5, so in units of concentration, microgram per meter cubed, and down here you have the relative disparity, so the percent difference. This bit on the left are the DACs, the bit on the right is the low-income population, and in the middle we have 2 ways of representing differences by race ethnicity. This is for all people of color, and this is for the most exposed racial ethnic group. So basically, if you're comparing across these different bars, what you see is on the left and on the right, this policy can help eliminate and actually even overturn disparities by DAC and by income. So in this aggressive and very aggressive scenario, these disparities can be eliminated in 20 years. Whereas in contrast, the disparities by race ethnicity are not. You see the air gets cleaner, the disparities come down a bit, but actually in relative terms, they don't come down, or in some cases they even increase, depending on how you frame this. So this is kind of what we've been saying all along. The air will get cleaner, but the relative disparities will not come down, even with these policies. Why is that? Well, there's a lot of reasons for that, but one reason is this. The Biden administration, which is doing probably the best they can, does not want to get sued over this. And they did not include in setting up which are the DACs, race ethnicity. If you look at their entire document, the word race ethnicity, to my knowledge, only appears once, and it says race ethnicity was not included when setting up the DACs. So race ethnicity was explicitly part of the problem when this problem was set up. All those decades ago, redlining, racial covenants were explicitly about race. If we're allowed to talk about race when we set up the problem, but now today we're not allowed to talk about race when trying to find a solution, that's going to make it much harder to find a solution. So I'm going to wrap up here. This is a call to action. That's a polite way of saying this is not okay. This stuff down here, this is not okay for various reasons. One is we can't have it be the case that looking out into the future, we're going to continue to not address or even worsen these disparities. It's also not great that the Biden administration, which is trying to do the right thing here, is spending tens of billions of dollars to address this and is probably not going to address the disparities by race ethnicity, at least according to our modeling. That's what we see. There's various reasons for that. Another reason is that the tools to do this kind of investigation, the types of data analysis, modeling, and data analysis are not widely used. And so the article that this comes from, what we argue is we need to do a better job. We in the air quality engineering community need to do a better job of setting up models and data so that they are designed to do this kind of analysis. So that it's possible to look at, hey, if we make these kinds of investments, what will happen not only to averages, but also to disparities. And right now our data and models are not really designed for that. I don't know what areas of science and engineering you work on or what areas of whatever you work on, but it may be the case that this is true in other areas of environmental engineering and other topics. That the data and models, if we want them to focus on disparities and understand disparities, we need to focus them explicitly on that and develop new ways of approaching those problems if we want to address them. So I'm going to end there. These are my 3 conclusions, which I started with. We don't all breathe the same air. The past is present. A lot of the reasons for this are historic. We didn't ask for these disparities. They were handed down to us. If we want to address them, we need to shed light actively on those disparities and orient our ways of thinking, our data and models on how would we address those disparities. With that, let me thank you all for being here. Thank my co-authors, especially the grad students who did the heavy lifting involved in the research that I presented here today. And I'm happy to take questions.